Hello. Madam, Bhavya is not arrived.
Yeah, he's not come.
Okay. Okay, if there are some questions from the people, you can ask. If when he comes, we can put to him. If there are some questions, you ask, unmute and ask, or you can type in the chat box.
Okay. Good morning to everybody. Am I audible? Hello?
Yes, sir, you're audible, sir.
I'm sorry I am a little late. Is it okay? Unitary, unimodular. I will explain what they are. Matrices. 2 into 2. 2 into 2 matrices. That is U. U means, of course, U. I hope you know. U dagger U equal to 1. Namely, U dagger is Hermitian conjugate, which is transpose and then take complex conjugate of every element. That is U dagger. And unimodular means determinant of U equal to 1. That is why they are called U2 or U3. These are 2 objects. We will go to 3 objects later. This is SU2 we are doing now. SU2 it's 2 by 2 and SU3 there will be 3 by 3. We will transform the 3 quarks UDS like that. And so that is the definition of the SU2. S means simple in a technical sense. If it is unimodular, then it is supposed to be simple. You cannot be factorized into another matrix times a Hermitian matrix. Okay. Now, in general, U can be written as exponential real numbers I equal to 1, 2, 3 real numbers. Taus are the Pauli matrices. Here repeated indices are summed over. I is repeated, so tau 1 theta 1 plus tau 2 theta 2 plus tau 3 theta 3. Repeated indices summed. Pauli matrices, I hope all of you know. In ordinary angular momentum space, they are usually called sigmas, but it is the same matrix. 0 1 1 0. Sorry, tau 1. Tau 2 is 0 minus I 0. Tau 3 is diagonal 1 minus 1 0 0. They are called the Pauli matrices, and they satisfy this commutation relation, which you can verify. Tau I tau j commutator is equal to twice I epsilon I j k tau k. Again k is summed over here. I and j are arbitrary one or two. Epsilon is a completely antisymmetric symbol, it is called. It is antisymmetric. Yeah. Is it clear now? I mean, are the letters big enough to be seen by you?
The subscripts are not.
Subscripts are not coming. Okay. So I will be more careful now. Epsilon ijk are antisymmetric, namely if you interchange any two.
Somebody's microphone is on, so there's an echo coming back. I think it's Sanbuga Priyan.
Can everybody mute their mics, please? Epsilon 1 2 3 is the same as minus epsilon 2 1 3. When you interchange two of the indices, it will become minus. And if any two indices are identical, it is 0. So that is the definition of epsilon symbol. I forgot to mention another important property of tau matrices is, I should write it big, the anti-commutator. Commutator is tau I tau j minus tau j tau I. This is tau I tau j plus tau j tau I, and it is equal to twice delta ij. Delta ij is called the Kronecker delta, which means when I equal to j it is 1, otherwise I equal to j then it is 1, otherwise it is 0. I mean, all this means is the anti-commute. If I and j are different, the anti-commute. Tau 1 tau 2 is the same as minus tau 2 tau 1 and so on, and the squares of them are unity, as you can check from here. If you put I equal to j, it becomes 2, so tau I squared plus tau j squared is 2, so tau I squared is 1 and tau j squared is 1. You should compare this with the angular momentum algebra, which is more general than this. Let me write it down. For the SU2 group, more generally, Ti is called the generator.
Ma'am, can you tilt the screen towards left a little?
Generator. Is it okay? T.
Camera towards left.
Is it okay now? I don't know. Maybe she's. Maybe she's not here.
Camera towards left. That will be fine.
No, she's not here. Let her come back.
Oh, okay, sir. Fine, sir.
Huh? So the generators satisfy the algebra Ti, Tj, commutator without 2, I epsilon I j k tk, again k summed over. This is called Lie algebra. Generators satisfy Lie algebra. U's form a group, but oh, here I forgot to mention how is exponential defined. Exponential of a matrix is simply defined by its series 1 plus a square, 1 plus a plus a squared by 2 factorial plus a cubed by 3 factorial and so on. That is the definition of exponential. matrix multiplication is clear, then you add them, and that is the exponential of a matrix is always defined through the series, exponential series. And if A is anti-Hermitian, A dagger equal to minus A anti-Hermitian, then exponential of A is unitary. This you can easily prove. That is why I have taken these anti-Hermitian, because all the taus are Hermitian, thetas are real numbers, and so this is Hermitian, but once I put I, it is anti-Hermitian. Exponential of IA is a unitary matrix, provided A is anti-Hermitian. These are the details which I missed yesterday. And these taus 2 by 2 matrices are called 2 by 2 representation of the generator. This is the more general Lie algebra, it is called. Madam, they are requesting that it should be tilted a little bit.
Ma'am, it is like
Actually, if you can
directly on the YouTube.
If you zoom it, it's okay, right?
Yeah.
Is it better now? This is called Lie algebra. U's themselves for arbitrary theta satisfy the rules of groups. They are called Lie groups. This is called Lie algebra. The generators satisfy Lie algebra. In fact, most of the time we will be using the Lie algebra only, not the group. And T I, the 2 by 2 representation is the Pauli matrices. It's called the fundamental representation. Fundamental representation, or the defining representation, because we define SU2 itself through the 2 by 2 matrices. But then more generally there can be higher dimensional representations of T. They are called representations. Mathematicians call them representations. Physicists would like to call them as multiplets. 2 by 2 representation works in the space of the doublet, and 3 by 3 will be a triplet, I equal to 1, and 3 by 2 will be I equal to 3 by 2 will be 4-dimensional representation, and so on. All integers, you can represent them by any integer. So these are matrices of higher dimensions, higher than 2. We already know about them. For instance, the SU2 Lie algebra can be represented by a 2-dimensional representation, or 3-dimensional, or 4-dimensional, and so on, all integers. And the corresponding notation which we used for isospin is, this is isospin half, isospin 1, isospin 3 by 2, and so on. All this we already know. And we also worked out the how to combine angular momenta, isospins of 2 particles. We already did it, but let me write it down again. This is a 2 by 2 representation. 2 is the fundamental representation. So consider 2 particles, one with isospin half, denote it by vector, the isospin vector, isospin space. And if you add a spin half to spin half, you can get either spin 0 or 1. Let me write like this. Or another way of writing it is 2 into 2 representation. There should be 4 objects, and they become a singlet corresponding to this and a triplet corresponding to this. So this is the way it is usually written. Okay. This is the group multiplication of group representation. And correspondingly, the wave functions can be written like this. For the I equal to half, there are 2 objects. I3 equal to plus half will be I3 equal to plus half will correspond to, let us call it alpha. This notation is used for ordinary spins also. This is spin up particle, and I3 equal to minus half V beta. We will denote like this. Then I can write down the wave functions corresponding to this singlet and the triplet, that you already know. First particle alpha, second particle also alpha, that is one thing. Corresponding I3 equal to plus 1, beta plus half, and the second alpha 1 beta 2 plus beta 1 alpha 2, that is isospin I3 equal to 0, then beta 1 beta 2 I3 equal to minus 1, minus half. So this is called the triplet representation. I3 I have already given, and all of them correspond to I equal to 1. Then I equal to 0, how do we get? You get the ortho here. To normalize them, since there are two state vectors, each of them is already normalized. So since we have added two of them, to normalize you have to put 1 over root 2. And this one is alpha 1 beta 2 minus beta 1 alpha 2. Again normalize it by dividing by root 2. Not 1 over 2, but root 2, because it is the squares. Now, normalization is always defined through the squares. This is I equal to 0, and I3 of course is 0. This is only a repetition of what I did yesterday, but I thought to be complete, it is better to do it. Now, I did one exercise in this last time, and I am going to repeat that exercise, namely, how to get antiparticles. What are the isospin properties of the antiparticle wave functions? Let me remove that part. Is there any question in this?
Whatever you have written on the right side
is
very small.
Oh, this has become very small, huh?
So you see the TI, commutator you have written
on
the left side.
That is the right size, huh?
That is the right side.
Okay. I will keep that in mind. This block.
If she is there, you can ask her to focus on the right side of the board.
Hello, Gayatri? Can you please? Yeah, this has to be. Is it okay?
Yeah. That's fine.
Okay. So has everybody looked at it? Can I rub it off? I want to write something else now. I want to ask, how does a doublet of antiparticles, how do we write the wave functions? This is again a repetition of what I did yesterday. Antiparticle transformation. Let us call this doublet wave function ud as psi. Then first form psi star. Psi star will be, because for antiparticle always corresponds to a complex conjugate of the wave function, u star d star. So these are not antiparticle wave functions correctly, because this transforms like an I equal to half object if you put this u here. That is the correct transformation property of an iso doublet. But you will find that this does not transform exactly like that. You have to do something to that. So I multiply by I tau 2. Remember, tau 2 is this. So if I multiply by I, it is 1 minus 1 here. So that will make it, first of all, this thing interchanges column and row. So this becomes a d star, this becomes u star. That is the correct way of writing, because remember u and d have I3 equal to plus half and minus half, and for the wave function the u3 equal to plus half should be above, u3 equal to minus half should be below, but d star is antiparticle to d, so d I3 d star is I3 equal to minus half. I'm sorry, d equal to minus half, so d star is plus half, so that has to go up. That is why this I tau 2 does that. But in addition, tau 2 puts a relative minus sign, so there has to be a relative minus sign. This is the correct transformation property.
In the last time when you discussed this, you have used instead of star a bar.
Okay, so let us do that. If you denote it as a particle, then maybe better to use bar, but actually it is a complex conjugate. Although I will use a say star here. This I asked you to prove as an exercise, but I myself proved it, so let us do that now. For that, it depends on this identity e power I tau. Now I am using a different notation. Tau I theta I summed over, I am calling it as tau dot theta, scalar product in isospin space. Prove that this is equal to, this is a very useful identity, cos theta by 2 plus I tau dot theta. I will define these quantities, where theta is defined as the magnitude of the vector theta, and theta unit vector is theta vector divided by the magnitude. That is the way unit vector is defined. So this you can prove, because by using this exponential series for this, all the even terms, remember tau 1 squared is 0, tau 2 squared is 0, tau 3 squared is 0. Using that, you will find that all the even terms are nothing but the series for cos theta by 2, and all the odd terms, there will be one tau only remaining. All the tau cubed, tau 4, 5 can be converted into tau basically. You cannot write down an arbitrary function of tau with all the terms collapse to a linear function of tau only, the constant plus a linear function of tau. So that is why a constant plus a linear function. I am not very, I don't know, something is wrong. So multiplication, there may be a 1/2 here also perhaps, I don't know, I am not sure. Please check that. Verify this. I have already given the proof, but please verify it explicitly. And e power minus will be, there will be a minus sign here. So prove that tau 2, I want to multiply the wave function by tau 2. So tau 2 exponential of minus I star means complex conjugate is equal to cos theta by 2 minus I will simply write down the result. This is equal to exponential of plus I tau by 2 dot theta into tau 2. You please prove this. How do you prove this? Again, you use this, and then you will have to commute, because tau 2 I have commuted this way. You have to commute tau 2 with tau star, but tau star, you remember, is tau 1, tau 3 are real, and tau 2 is complex, pure imaginary. So tau 2 star is minus tau 2. Use that fact, and this tau 1, tau 2, tau 1 and tau 3 with tau 2 will anti-commute, so that will produce a minus sign. Whereas for tau 2, since it is tau 2 only, it just commutes with tau 2 itself. But that minus sign comes because of what I said, because tau 2 is pure imaginary. Because of that, all the overall minus sign comes. So just using this, since I have already written this, okay, let us write down the equation in a different way. The transformed psi is e power this, but I want transformed complex conjugate of psi, which is equal to e power minus I tau star theta psi star. Just taking complex conjugate of this equation. Now multiply by I tau 2. Okay. Now use this result, because in this what am I doing? Psi prime star is this. Just multiply by tau 2 I said. So I suppose this is correct. I have written down the final result without. Cancel this. Multiply this by tau 2. I am repeating it. Tau 2 e power I tau by 2. I have simply multiplied, that is all I have done. But actually I want to take this also and multiply by tau 2. So tau 2 psi prime star is equal to tau 2 e power minus e power minus I tau star dot. I am making so many mistakes here, you please check to yourself into psi star. But this tau 2 you try to commute, this will become plus and star will get removed and tau 2 will come to the other side. So tau 2, I am sorry, tau 2 I have tried. So this is the important equation. So tau 2 psi prime transformed in the transforms in the required way. Required way is that psi prime is the required way. For an isodoublet, it should be plus and all taus only will come, and that is what happens here. So it is tau 2 psi star which behaves correctly as an isodoublet. So tau 2 psi star goes to tau 2 psi prime star under the SU2 rotation. You multiply by I does not do anything. That is just for convenience. I tau 2. So I tau 2 psi prime star is the correct isodoublet, which means first they have to interchange the upper and lower components and then put a relative minus sign. So this is the antiparticle doublet. I think I had done up to this last time. So I have essentially repeated last time's lecture with maybe a little bit more explanation and correcting the mistakes last time. Okay. If there is any question here, you can ask me, because this is a simple exercise in dealing with 2 by 2 matrices, and it is good to do it yourself. Although whether you have understood or not, I have said what I wanted to prove. I want to prove that this I tau 2 psi prime star is the correct, has the correct transformation property, namely psi goes to psi prime, which is equal to u, which is this. If it does like that, then it is I tau 2 psi star, which has the correct transformation property. So this is the antiparticle wave function, because I tau 2 psi star goes exactly in this direction, just like this with this. So I tau 2 psi star is the correct iso doublet wave function for antiparticles. Just remember this point. First of all, because of I3 getting reversed, you have to flip the upper and lower component, then put a minus sign. If you remember that, that is enough. I have already used it in constructing the quark model for mesons. You might remember that. I used a relative minus sign. The same thing I am now proving. Okay. So let me now go over to SU3.
This transformation physically means that I cannot have a particle with U and D bar, a composite particle where a particle of U and D bar.
A composite particle of just U and D bar, is it?
Yeah.
U and D bar, what you have to do is you have to either symmetrize or anti-symmetrize. If you symmetrize U D bar plus D bar U, that will give you a singlet from because both U and D are D bar also isospin half. Isospin half plus half will give you isospin singlet as well as isospin triplet. Isospin singlet I have rubbed off, remember in terms of alpha and beta I had written down the functions. Remember in the singlet the relative minus sign was there, it was antisymmetric. In the triplet it was plus, but that was if both the particles are particles. If one of them is antiparticle, this extra minus sign here makes with the plus sign as singlet and minus sign as triplet. Remember for pi 0, which is a triplet in isospin, I had written minus sign. For eta, which was a singlet under SU2, I had written plus sign. So please remember that. I had noted down that difference. If you just combine two spin isospin halves, you will get plus sign for triplet and minus sign for singlet. But if it one is particle and another is antiparticle, it is just opposite. That's all. That's all you have to remember. But if you write, I think Satya asked the question, what about UD bar? So you simply write that. That will not have a unique transformation property because it is a combination of singlet and triplet, because UD bar can be written as half of the singlet wave function plus half of the triplet wave function. You can write because the minus sign will cancel. Okay. If you just write down UD bar, it will be neither a singlet nor a triplet, but a superposition of both. It will be a superposition of pi 0 and eta particles. If you want to have a pure pi 0 wave function, you have to write down either symmetry, either the other one and with a minus sign or plus one. Okay.
When you listed these mesons,
yeah,
pi plus you have written as D bar U.
Pi plus I wrote down as what? I think
D bar U.
Yeah.
And pi minus as du bar.
Pi plus was U D bar. Did I write like this?
Yes.
U equal to I3 plus half, and D bar is also I3 plus half. So this is correct. Whereas let us repeat that. Don't mind repeating it. The meson quark compositions for mesons. I'm redoing it. The mesons is quark composite. For pi plus, I wrote down as U D bar. Why? You can see charges match 2/3 and plus 1/3. D is minus 1/3, but D bar is plus 1/3. So total charge is okay. Isospin plus half. This is also plus half. d is minus of d bar is, so this is all you have to write, you cannot write down anything more, just cannot write down anything more. And pi minus as I think I wrote as a d and u bar, again you can check the charge and I3, and pi 0 is the combination of two particles because pi 0 will be u bar. First of all, I3 equal to 0, so you have to write u bar because then I3 is total 0 and charge also is 0 for this. But dd bar also has the same property, that is the problem. You have to write down a linear combination of these two. But what linear combination? I am saying I have to put a plus with s 1 over square. Then only it is correct, because then only it will be a member of the iso triplet. If you put a minus, it will be a singlet. It's the other way, right? It is just exactly the reverse because of the relative minus sign here. When I wrote down for the two, suppose I want to form a composite of UU, of course such a hadron does not exist, I will tell you the reason later. If you do this, you will write down correspondingly here U, no, let us not go over that, that will only confuse the issue. So 1 over root 2 will be the orthogonal combination UU bar plus DD bar. If it had not been antiparticle, just particle, it would have been minus here and plus here. But I am saying that the signs get flipped because of that minus sign. That's all I am saying. Okay? And k plus k0, k minus k0 bar, there is no complication. Complication comes only when there are these this kind of objects, diagonal objects. So shall I go to SU3 now? We can always come back to it anytime. The other question I wanted to ask was, you can always ask me in email, but you can look at my lecture. I hope all of you are able to look at my lectures at leisure because they are all being recorded. I don't know whether they are all being sent. I think Satya, they are there in the YouTube channel. Oh, they are there in the YouTube channel. So you go back anytime and you can ask me questions at any time. So let me go to SU3 now.
Sir?
Yeah.
Sir, I haven't watched the fourth lecture completely.
Okay.
Still I am asking.
Yeah.
But whenever you are writing those UD in column matrix,
yeah,
those U and D represent the wave function, right?
You can either in a heuristic way you can call them particles, but actually mathematically they are the wave functions. The wave function of U quark and the wave function of the D quark. Yeah.
Sir, one more thing, sir. When you are writing that in that column form,
yeah,
what does it mean completely? Like that side, like you are writing U and D.
I am writing as column, two-element column because it is a doublet, iso doublet, and it transforms under a 2 by 2 unitary matrix. So to transform them properly, I have to write it as a column matrix.
Okay, sir.
Yeah.
Sir, and when you are doing this transformation,
yeah,
what does that transformation actually mean?
See, ultimately we are going to construct the theory of these particles, and the theory of particles are invariant under these unitary unimodular transformations, 2 by 2 transformations. So it's a symmetry of particle physics. That is why we are studying this now. In fact, when I introduced it to the particles themselves after Heisenberg's idea, I simply wrote them heuristically like spin up, spin down, iso spin up, iso spin down. That is the way I introduced. But the real mathematics of that is the SU2 group, and the SU2 group, see, ultimately we have to look at the equations of motion of these particles, or more properly the Lagrangian. I will come to Lagrangian, I hope later I will come to Lagrangian. And the Lagrangian is invariant under this unitary transformation. And in order to see the transformation property of Lagrangian, we have to know the transformation properties of all the objects which come inside the Lagrangian, or actually more properly U and D I will use as the field operators for the U quark and the D quark. In quantum field theory they become field operators. In quantum mechanics you can call them wave functions, But correctly speaking, we need quantum field theory to understand particle physics. Quantum field theory is the only correct language for particle physics. Ultimately, I am tending towards that. I will give you a little bit more information about quantum field theory in an elementary way, maybe in the next lecture or so. Then you will see that these are all field operators, and they come in the Lagrangian as dynamical quantities, and we have transformed each of them, and when we make the transformation, you find the Lagrangian itself does not transform, it is invariant. That is the meaning of any symmetry, any SU2 or SU3 symmetry which we will use. Symmetries play a very important role in particle physics, not only in helping to classify the particles into multiplets, but I mean, they are really true. The interactions are invariant, not completely invariant. There is breaking also. We will talk about the breaking also. Actually, I talked about the breaking already. SU2 is broken a little bit. That is why proton and neutron mass are not exactly the same, about 1 or 2 MeV difference. Whereas when you come to SU3, the between the octet of particles, 2 nucleons, proton and neutron, and 1 lambda and 3 sigma, sigma plus sigma minus sigma 0, and cascade 0, cascade minus, the octet of particles, masses are not the same. They vary roughly by the order of 200 MeV. So in 1000 MeV, 200 MeV, so 20%. 10 to 20% breaking of SU3. Then nevertheless, it is useful symmetry because it is through this the quarks were discovered. There is another SU3 symmetry, the color symmetry I already introduced. I already introduced the color last time, and we will have an SU3 on that color, the 3 color indices. So every quark, when I say U and D quark, there are 3 varieties, U1, U2, U3. There are 3 colors. And that SU3 color symmetry operates on these, and that is gauged. It becomes a gauged interaction like electromagnetic interaction, and that is what is used to construct the standard model. So that SU3 is more fundamental than this SU3, but the mathematics is the same.
Okay, sir. Thank you, sir.
Yeah. So SU3, you go in parallel steps. I will just define SU3, maybe I will take about 5 minutes more, and then we will come back after half an hour to discuss more details. So I go in parallel steps like UD, we have now 3 quarks, SU3, U, D, S. By SU3, we transform them again by a 3 into 3 unitary matrix now. U prime, D prime, I don't know whether I am using the same notation, by U, UD, yes. So U is a 3 by 3 . I forgot to mention one thing. When I wrote down U equal to e power I tau theta by 2, I could have multiplied by another e power I theta 4. There are 3 components, theta 1, theta 2, theta 3. So just arbitrary phase pattern. Theta 4 is arbitrary real number. This is also unitary, you can easily check, but it is not unimodular. Determinant of this, so I forgot to mention that if U is e power A, then determinant of U, please verify this. This is a theorem in matrix algebra, exponential of trace of A. The diagonal sum is called trace. So because of this, if you write down traceless matrix as a determinant, because unimodular means determinant U is 1. So that is why all the taus which we wrote down are traceless. You add the diagonal elements, it is 0. And this one is like 1, and diagonal element, I mean the trace is not 1. Trace is not 0, and so the trace of A is not 0. The determinant of U equal to 1, unimodularity means trace of A equal to 0. Because of that, this cannot be written down. Theta 4 is here. That's why there are only 3 parameters, not 4 parameters in the SU2. But if you are talking about U2, only unitarity and no determinant of not unimodularity, then you can add this. That is the most general 2 by 2 unitary matrix. That will define U2, not SU2. We are not using U2 here. We are using SU2, the simple group in which the modulus is 1. So please remember that. These are all small technical details, but explains why it is called SU2 and so on. Okay, so now I want to write down the most general 3 by 3 unitary unimodular matrix, which I am going to write down now, which is exactly analogous to this 2 by 2 matrix. So this is 2 by 2. This is 3 by 3. Unitary unimodular, you can write down, and that is U equal to exponential of lambda I theta lambda I by 2, again exactly like the theta I are 8 real parameters. So most general SU2 transformation contains only theta 1, theta 2, theta 3, 3 parameters. If you know your angular momentum theory, you will see that angular momentum corresponds to rotation, and rotation in 3 dimensions is defined by 3 angles, the Euler angles. If you have done rigid body motion in classical mechanics, you will know, like the Euler angles, 3 angles. Those are the 3 parameters. Okay, parameters can be chosen in different way, either Euler angle or like this. In contrast, here there are 8 real parameters. I equal to 1 to 8. And these lambdas also satisfy exactly the equations like the Pauli matrices. Lambda i's are, you can say, generalization of the Pauli matrices into 3 by 3 matrices is equal to, actually lambda I by 2, if you take they are the real generators, is equal to Fi jk lambda k, again k summed over here, lambda k by 2, and you can multiply by 2 everywhere, I think, but 1 2 will remain here, so it becomes 2. 2I also is there, right? I. This I is square root of -1, not to be confused with this I. So lambdas satisfy this. Lambdas are called Gell-Mann matrices. The 2 by 2 Pauli matrices, these are generalizations of those which Gell-Mann generalized it to Gell-Mann matrices. They satisfy these commutation relations. What are Fij? Like epsilon ijk, these are also completely antisymmetric, but they are not as simple as epsilon ijk. We will not need them, but just for completeness, let me write down F1 2 3 equal to 1, F1 4 7, F2 4 6, F2 5 7, F3 4 5, F5 1 6. This, if you cannot copy here, you can take it from any book in particle physics will give this, or the particle data group information. I hope you have gone to the Google to look for it, particle data group. That will give a small essay on SU3 with all these information will be there. All these are equal and equal to half, and then F4 5 8, F6 7 8 equal to root 3 by 2. All other f's are 0. Again, if any two of them are equal, they are 0, and they are antisymmetric. F417 is minus half, and so on. All others 0. That defines this. So, these are Gell-Mann matrices. Maybe I will go for another 5 minutes. I think since I started a little late, we will take another 5 minutes and define the SU3 completely, and then we will leave it at that point. More generally, okay, I did that for SU2 also. More generally, U should be written as exponential of I Fi theta I, again I summed over, and Fi are called generators of SU2, SU3, and they satisfy commutation relations. I mean, with half I wrote down the original commutation relation. Those are the commutation relations of F. Not epsilon, but this small l, okay. So that is the Lie algebra. What we have got is the 3×3 representation, namely the fundamental representation of this algebra is what we used to define SU3 itself. After that, we generalize the notion because this is connected with something one of you asked. In the Lagrangian, there will be fields not only which correspond to the triplet representation like the quarks, but there will be octet representation particles and so on. And for octet representation, we have to use F's which are 8-dimensional. So, they are the representations, and 3 is the fundamental representation, triplet is the fundamental representation. There are other representations which I have talked about earlier in the very beginning itself when we introduced the particles, but let me go over it here more completely and then I will stop. Representations are multiplets. Representations of matrices, but if we write the wave function, it will be written as a column vector. What are those? This is 3, and it turns out 3 star is another independent representation. This is another only important difference between SU2 and SU3. When I took complex conjugate of U and D doublet, after some simple manipulation, it also behaves like a doublet. There is no, I mean, there is a doublet representation 2, but there is no separate 2 star. 2 star behaves, 2 star is identical to 2, provided you write down the correct multiplet structure. But that cannot be done for the higher groups. 3 star is different. So, it is although it is the same dimensionality, but it is different. So, antiparticles, anti-quarks will behave like 3 star, and it is a different representation. The U star cannot be related to U in a simple way. You remember in the case of Pauli matrices, because of the anti-commutation relation and so on, here there is no anti-commutation relation, please remember. No anti-commutation relation for SU3 generators. Then next is 6, then 8. Octet is what I used. In fact, that is what originally Gell-Mann, Neyman made SU3 famous by choosing the octet representation for the 8 baryons and 8 mesons, remember. Then he introduced the tenfold representation for all the resonances, n star, delta, delta, sigma star, cascade star, and it had to include one more particle, omega minus. He predicted that particle, and that particle was experimentally discovered, thus establishing Gell-Mann SU3. That's all old story, I am repeating it. Then there are 27 and so on. So, in contrast to SU2, where the representations are dimensionalities of all integers, that is not true here. Here you have to do the mathematics. Of course, all these mathematics has been completely worked out now. Just one more point I will make and then we can quit. After that we can go to something else. Yeah. So, let me just make one more point. rather 2 more points. Just as I gave I wrote down the Pauli matrices, which are very easy. Lambdas also can be written down. It was originally given by Gell-Mann, and these are generalizations of the Pauli matrices. In the 2 by 2 space, in fact, they are all Pauli matrices. Remember, this is tau 1, and here it's all 0. Okay, and lambda 2 is like tau 2, so it should be 0 minus I 0 and 0 0 0 0 0. Lambda 3 diagonal 1 0 0 minus 1 0 0. And 4 and 5 also are Pauli matrices, but not in 1-2 space, but 1-3 space. So it should be 0 0 1. First of all, let me put the zeros here. This is 1 3, and this is 3. Again, made it wrong. This is 1 3. Yeah, 0. There should be one more. Yeah. So if you look at 1 3, it is like tau 1. Similarly, lambda 5 is like tau 2, but again in 1 3 space, so I have to write 0 0 minus I 0 0 0 I 0 0. Lambda 6, that will be in 2 3 space, right? Yeah, 2 3 space. 0 0 0. So in 2 3 space it is like tau 1. Similarly, lambda 7 in 2 3 space will be like tau 2. There is still one more matrix that is also diagonal like this, and that is called lambda 8. That's all. Remember, all the matrices have to be traceless. That is why 1 1, if you put, you have to put minus 2. Then because unimodularity will demand that all the lambda matrices are traceless. One more thing I want to note, there are 2 diagonal matrices. One more thing, I could have mentioned it in the context of SU2. Remember, in SU2 only the I3, the third component, is diagonal. So because of the non-commuting nature of the different components of I, like angular momentum, only one component can be specified. The total angular momentum, which is called the, I squared, I1 squared plus I2 squared plus I3 squared, and one component. We normally choose it to be I3, that is why tau 3 has been chosen to be diagonal. So that is the diagonal quantum number for SU2, which distinguishes the different members of a multiplet, like pi plus, pi 0, pi minus, are distinguished only by I3. Okay, otherwise all of them have the same isospin. Now, in the space of 3 by 3 matrices, you can write down only 2 independent diagonal matrices. In the space of 2 by 2, only one diagonal matrix was possible, that was the Pauli matrix. But in the case of 3 by 3 diagonal matrices, only 2 are possible, and these are the 2. And so you can see that in the multiplet structure, when we talked about it, isospin multiplet we simply wrote down as a line p and then r pi plus, pi 0, pi minus, and so on. Whereas for the SU3 multiplets, like the octet diagram, the hexagon, it was a 2-dimensional space denoted by I3 and Y hypercharge. So these are really the I3 and hypercharge, apart from a factor of half or something like that. I don't know what it is. So remember, this is the UD space, which is same hypercharge, and the S has strangeness, and so it has a different hypercharge. So this is basically hypercharge apart from some factors. So I3 and Y, which we used to exhibit the multiplets, come with definite numbers for lambda 3 and lambda 8. So these are the diagonal quantum numbers. One more point I will make and then quit. I can use this space for that. See, for SU2 was determined by 3 parameters, the 3 angles I said, and in terms of this it came as that theta 1, theta 2, theta 3, because the number of generators were 3, and for SU3 the number of generators were 8. How do we get these numbers? It is very easy to see that. You have to just work out this number. SUN, if you look at SUN, let me write down SUN. Number of generators. How do you work out? Remember, these have to be a corresponding thing for SUN. These have to be Hermitian traceless matrices. How many independent numbers are there in n by n Hermitian traceless matrices we want? How many independent matrices you can construct? Those will correspond to the number of parameters which define the group element. Hermitian traceless matrices. Hermeticity. If you count, if you look at the n by n matrix, Hermitian matrix means all the diagonal elements have to be real. Remember that. And all the off diagonal elements will be complex conjugates of each other. That's all. So diagonal elements. So let us count like this. Total number is n squared. No, let me look at the diagonal number. They are all real. So n. I don't have to write 2n. And look at the off diagonal elements. Off diagonal elements, how many there are? If you look at n squared, and we have to remove this n, and then divide by 2, because the off diagonal elements are complex conjugates of each other. You can see this is the correct number. So n and n cancel. That is Hermitian. Then tracelessness, I have to remove 1, because there is one condition on the diagonal sum being 0. So this is the actual number of generators. In SUN. That is why for n equal to 2 it is 3, for n equal to 3 it is 8. These are the number of traceless matrices, and I already mentioned how many diagonal matrices can be constructed. That also you can easily work out for arbitrary SUN, but we are not going to anything higher than SU3 in this lectures. So I will stop here. So maybe we will come back in 10 minutes. Okay. So I will come back in 10 minutes.
Yeah.
And you can ask questions when I come back also. After that, we will go to the next topic.
wait one minute, wait one minute. எத்தனை மணிக்கு வரீங்க? 2 மணிக்கு போயிட்டு சரி அவங்க மும்பைக்கு வரதுன்னா நீங்கள் 4-5 மணிக்கு ஃப்ரீ வரீங்க. சரி வாங்க வாங்க.
மேடம் ஸ்கேன் பண்ணி
ஸ்கேன் பண்ணி உங்களுக்கு
ஸ்கேன் பண்ணி மேடம். Okay, so shall we start? If there are any questions, you can ask me. Step 6 now.
Good morning, sir.
Yeah, good morning.
Sir, in that you have given relation for calculating number of generators, right?
Yeah.
N square, n plus n square minus n minus 1.
Yeah.
In that you have told that if it is Hermitian that the elements which are off diagonal
Yeah.
has to be same, right? I mean,
Yeah.
it has to be Hermitian conjugate.
Yeah, correct.
So that should be a division of number 2. But in
Yeah,
the formula,
but remember the number of real parameters is twice because each is in general a complex number. So that 2 and 2 cancel.
Okay,
Yeah,
okay.
yeah.
Thank you, sir.
Yeah. Okay, now SU2, SU3, the mathematics of it I have already completed. Now I want to discuss briefly what are called heavy quarks. Apart from U, D and S, 3 more quarks were discovered in experiment. And I want to say a little bit about that. This is what? Lecture 6. Charmed quark C, the so-called bottom quark B, and the top quark T. These are called heavy quarks. And before that, for the light quarks U, D, and S, light quarks, the masses are of the order of, this is about 4 MeV, this is about 8 MeV, this is about 30 MeV. Please remember that. In contrast, these numbers are very large, 1.5 GeV. This is mass. This is about 5 GeV. This is the heaviest, 174 GeV. Since it was so heavy, it was discovered only in 1995 in the Fermi laboratory. They had completed all the quarks. Now, the discovery of these two are interesting, so I am going to talk about it a little bit. And those are the discovery of two particles, two hadrons called psi and epsilon. This is the Greek epsilon. 1974 November. It's called the November Revolution because of what I'm going to say. You will see psi was ultimately identified as a bound state of the charmed quark and its antiquark, CC bar. And mass was 3.1 GeV. And how was it seen? It was seen as a narrow peak in E plus E minus collider. Annihilate through the one photon is emitted, E plus E minus, and E plus E minus high energy machines have been existing for more than 30 years now, photon, and then many hadrons are produced. In this, when they calculated the cross section for this, again they got a resonance, but this is not the delta resonance or anything. It is very narrow, very, very narrow, almost like a delta. And the half was very narrow, half it was about 60 keV. Remember, it is not MeV. Such a heavy particle will have many decay channels. Remember, delta itself had a half width of 100 MeV, and when you go to this much energy, I would expect it to be about 1000 GeV, about 1000 MeV, about 1 GeV width it should come. It should come like this. Instead of that came. It was like some anthropologists when they went into a forest, a particular corner of a forest, they found a group of human beings who lived for more than 10,000 years. It is somewhat like that, more than 10,000 or 100,000 years. The discovery was like that, so that is why I call it revolution. Finally, it was resolved. How was it resolved? That's another story. Asymptotic freedom I have already mentioned. In asymptotic freedom, the interactions at high energies and high masses, in the strong coupling becomes weak. That is what is asymptotic freedom. I think I already mentioned it, but I will perhaps say more about it later. And asymptotic freedom has already been introduced by the fact that they could see quarks in deep inelastic scattering. I think I already talked about it briefly. Deep inelastic scattering showed that proton is made up of point particles, like the Rutherford scattering. In addition, those point particles behaved as if they are free. As looked at by a high momentum probe, like high momentum photon, it looked like free. That is what's called asymptotic freedom. It was because asymptotic freedom, it was recognized only the strong interaction has to be asymptotic free, and the only asymptotic free quantum field theory is a non-abelian gauge theory. It cannot be an abelian gauge theory, non-abelian gauge theory. Since the color degree of freedom was already there, they just jumped on it. QCD was formed. That is how QCD came. So by that time it was known. So, and this 3.1 GeV is not asymptotic energy, but it's still large compared to, let us say, 1 GeV, which was the typical energy of all the other hadrons, about 1 GeV or less. Compared to that, this is a lot. At this, the coupling of this CC bar to other hadrons has become already weak. And that is why, remember, width depends on the coupling constant as well as the phase space and so on. And since the coupling constant has become small, its width is, instead of, let us say 1 GeV, it has become 60 keV. That was the resolution of this remarkable result. Not only that, CC bar exists as ground state, then excited state, so many states. It was almost like hydrogen atom. So this system was called the hydrogen atom of particle physics. Because now they could see a spectrum of particles which are bound states of CC bar, like the bound state of electron and proton, giving you hydrogen, ground state, and its excited state. And in fact, many people got convinced of the existence of quarks only after this discovery, and they could explain all the many higher excited states as excited states of the ground state, exactly like hydrogen atom. So this discovery was made by Burton Richter, B. Richter, and and also I think the other guys, same thing. Independently they discovered it, so they got Nobel Prize very soon after 1974. Now we have bound states of C with the light quartz, and this is called the charmed hadron D, and C bar U will be called D bar, and their excited states also are known. C U bar or C D bar, also. One heavy quark and one light quark, so that is D, and then DS also. That will be C S bar. Yeah. U bar, D bar are called D bar. It will be an isotope doublet because C itself has isotope 0. Only these light quarks, these are the only particles that have isotope. This is isotope singlet, and all these have isotope 0. Please remember that. So this is an isotope singlet only. They have found charmed composite objects even with baryonic quantum number called the lambda C. Remember, our original lambda was 2 light quarks and 1 strange quark, whereas this one will have 2 light quarks and 1 charmed quark, lambda C, and correspondingly sigma C. All these have been seen. This discovery was repeated a few years later. That is what led to the B quark.
So what is this capital D and capital U bar?
D will be Cu bar, and so this is Cu bar, and this will be antiparticle, so this will be C bar U. Okay. But you can put either U bar and U or D bar and D.
Okay, sir.
So there are many particles, some with charge 0, some with charge 1, charge -1. All these particles are there in this common notation. Whereas here I think there is only a single one, C and this bar, nothing else can be made. That was the discovery of psi. What about the discovery of epsilon? Repetition of the study. Epsilon was identified as, this again was seen as a narrow resonance, almost like that. Maybe the width was a little larger. Repetition of the study. Repetition of the psi particle. Again, many bound states, many excited states are seen. And then you also have, actually psi is called a hidden charm because charm quantum number itself is 0 here. You can give a quantum number for charm also, anything which is charm quantum number, but that gets cancelled by C bar, whereas these are not hidden quantum numbers, hidden charm. These are explicit charm particles. Similarly, this is a hidden bottom quantum number, and here they are explicit. B bar will be similarly B and D bar, B and U bar, and their antiparticles, namely B bar D. And almost a repetition of that. Correspondingly, there will be strange thing also. BS bar. That is B discovery. This is C discovery. What about T? T discovery, the story is very different because bound states of T quark. Oh. Yeah. So some part of this will be missing. bound states of T quark do not exist. What is the reason? Reason is again the same as asymptotic freedom. Because of that, at such high masses, the strong coupling has become so weak that it is not able to bound. It will take long time for the Bohr orbit to collapse into a bound state, and by that time the T quark decays, and T quark being very heavy, even by weak interaction, because the phase space is very high, 174 GeV particle, the T quark decays by weak interaction. So it is through the weak interaction T quark has been seen, namely the experiment, I think Tevatron experiment. So let me draw a schematic diagram. Asymptotic freedom. Because of asymptotic freedom of the strong coupling, T quark does not get bound to any other light quark, so T has to decay. T quark seen only through weak interaction, weak decay. T will decay into B and electron and the corresponding neutrino, or muon and the corresponding neutrino. So in the PP collision, so many other things are produced, but the T quark of course, I mean, I don't, in the lifetime is still very short because of the high mass, and so what you will see are the signatures for the B quark associated with an electron and another B quark associated with the mu, and that is why T and T bar will be produced in the PP machine. Tevatron, 1 TeV proton and 1 TeV proton. It existed in Fermi lab for a long time, and its major discovery was this top quark discovery. So only now I am talking about asymptotic freedom. I had not talked about it earlier. I briefly mentioned it, so let us talk about it. Okay, this is the story of heavy quark, but the story of heavy quarks is connected to asymptotic freedom. That is why both the psi and epsilon come as narrow peaks. But that asymptotic freedom itself was discovered in deep inelastic scattering. So let me talk about it a little bit. That is a very important subject which helped to understand strong interaction itself. QCD itself came from that. That I will call seeing quarks. It is not directly seeing, but indirect. Deep inelastic scattering, DIS it's called. It's an important subject in particle physics. It's deep in the sense that the momentum transfer imparted to the hadron from the electron, it is actually electron-proton scattering. But the electron is accelerated to very high energies, and it imparts very large momentum transfer to the hadron. Electron, a proton. Proton is a stationary target, a hydrogen target. How do they interact? Through electromagnetism only. So through the exchange of a photon, electron comes out. Yeah.
Camera has to be rotated to the left side.
Left why? This is just the exchange between the electron and the proton. I have to rotate this, you are saying?
No. Camera has to be.
Oh, camera. Sorry madam, can you again rotate? So I will write that side. This part you cannot see right now, is it?
The electron proton we cannot see.
So I will move it a little bit until she comes. What is deep elastic scattering? This is okay?
Yeah.
Electron, proton, electron, initial electron and final electron. It emits a photon and that is absorbed by the proton, and it is a very high energy, it is a virtual photon, but a very high energy virtual photon. Its momentum transfer we call q squared. This q is very large, that is why we call it deep elastic scattering. And what is q? Q is, let us call this the initial momentum of the electron, final momentum of the electron. Q is pf minus pi. All these should be 4 vectors, energy as well as momentum are subtracted. Then many hadrons are produced. Actually, it is a very complicated process. But if you ask a question, don't look at the hadrons, look at only this energy and momentum, and then study this cross section as a function of this q squared only and the initial energy. Then you find some remarkable simplicity comes. The whole cross section looks as if it is a superposition of cross sections of this object, not on proton but on point objects, point particles which behave as if free, they exist within the proton. The whole cross section could be decomposed into a sum of elementary cross sections of electron scattering on some objects which behaved like free particles. So these experiments were done in SLAC, Stanford Linear Accelerator in California. The later part of, I think they started in the middle of 60s and they continued into later part of 60s, like 1967, and continued. So what they saw was that the cross section can be understood by thinking of proton being made up of point particles as well as free particles. Oh yeah, this itself I should not have written. So they discovered that proton is made up of point particles and free. This point particle discovery inside the proton is like the discovery of Rutherford. You discovered by alpha particle scattering on gold atoms that gold atom had point particle nucleus. It is like a repetition of that history, like the discovery of the nucleus itself. Here we are probing the, he was probing the atom, and here we are probing the nucleon itself. Nucleon also is made up of not one point particles, many point particles. The other thing is they behaved as if they are free. Whatever point particles make up the proton should be strongly interacting, but as observed through very high Q photon, as observed through high Q squared probe, the constituents, whatever they are, behaved like free particles. That is the discovery of asymptotic freedom. That is at very high energies, high Q squared, these point particles are behave like free. The people who made this discovery in SLAC, I can mention some names. I don't know whether I remember. I don't have those names here. Friedman, yeah. Friedman, Taylor, I think there is one more person got Nobel Prize for this discovery. Of course, the importance of this was discovered only much later by the Nobel Committee, and they gave the prize, although the discovery was made in late 60s. So, theorists began to search for theories which are asymptotically free. Not every quantum field theory which we can construct is asymptotically free. Only non-abelian gauge theory is asymptotically free, and that discovery was made by Gauss, Wilczek, and Pulitzer. That was an important discovery in quantum field theory. Yeah.
What does this mean by asymptotic freedom?
Asymptotically high energies, the particles behave like free particles. That's all.
Okay, sir.
That was what was called asymptotic freedom. The discovery was that only non-abelian gauge theories, I don't know whether I have defined them, we will talk about them later, what are called Yang-Mills theories. Non-abelian gauge theories had been constructed by, I think on the very first lecture, if you were listen to my first lecture, I had a elementary discussion of non-abelian gauge theory. We will take up that later. Only non-abelian gauge theory is asymptotically free. This discovery was made by Gauss, David Gauss, Wilczek, and Pulitzer. These people worked together. Pulitzer was independent. That was around 1972, and they got Nobel Prize for this much later. But as soon as these people wrote this, Gell-Mann came. Gell-Mann, Fritz, and Lloyd Taylor, I think. Lloyd. Here I forgot to mention all the names. I think Friedman, Taylor, and Kendall. They are the experimenters who made the discovery of asymptotic freedom, and the theories who constructed the correct asymptotic, identified the correct asymptotic free theories are these. And since non-abelian gauge theory was needed, you have to search for a non-abelian group and some object on which that non-abelian group will operate, and that was already known. I told you when we constructed the quark model wave functions for the baryons, the excited baryons, in particular delta I use as an example, the wave function will be symmetric and violate Fermi-Dirac statistics unless you have another wave function multiplying it which is antisymmetric, and that was in the color space. In the color quantum number, the wave function is antisymmetric, so Fermi-Dirac statistics is restored. And so quarks have another degree of freedom. Although I have been writing as U, D, etc., I have to put an index on U, U alpha, alpha going over 1, 2, 3, the 3 colors hereafter. So that was the birth of QCD. I think Gell-Mann named all these objects, quarks, color, quantum chromodynamics. That also same year, I think, 1972, quantum chromodynamics. That became the theory of strong interactions. SU3 color. To distinguish from the SU3 I talked about earlier, on which operate, that SU3 operates on UDS, the light quarks, the 3 light quarks, that is called SU3 flavor, and this is SU3 color, gauge theory, and it has to be a gauge theory. Okay. Just one more discovery which happened around this time. Yeah? Sorry, there was a question? Or actually sometime later, the heavy lepton. Let me say briefly about leptons now. We will talk about leptons in more detail. I will talk about weak interaction. I have not talked about much. I think after this I am going to talk about weak interactions. heavy lepton. So far we have talked about electron, mu, and neutrino also we mentioned. There are two kinds of neutrinos corresponding to each of them. I will talk about neutrinos separately to tell you what is the difference between nu e and nu mu and so on. Now I am talking about a heavy lepton called tau, heavy lepton discovery, and that happened like this. Again, E plus E minus collision. E plus E minus means the intermediate state has to be photon only, and it produces tau plus and a tau minus. Tau plus decays let us say into electron and 2 neutrinos. Nu tau, so that has another tau, another kind of neutrino. What is the difference between all these we will come to later, and tau minus also analogously. This could be mu also, so here I put mu, and so mu minus, so mu bar, then I have to put. What is the difference between nu e and nu e bar and so on, all those we have to discuss, and this has to be nu tau bar. So the experiment this time sometime in the 80s, late 70s or early 80s or early.
This diagram,
Yeah.
when you read, because it is not.
Yeah, E plus E minus come and collide and give a photon, virtual photon, and the virtual photon materializes into two particles, tau plus and tau minus. And tau plus, tau minus, tau plus decays into an positron and 2 neutrinos, put them as 2 neutrinos, and tau minus also decays into mu minus and this. This could be mu plus and E minus, or both could be mu's, both could be E, all these were seen, and they were seen in this experiment by Martin Pearl, and he got Nobel Prize for this again. Okay, that is the story of the tau lepton discovery. So now that I have introduced all the elementary particles with which standard model will deal, let me summarize that. Heavy quarks I talked about, heavy leptons we talked about, so everything is complete now. We have 6 quarks and 6 leptons. We write them as doublets because they are isospin doublets, UD, similarly CS, and similarly T and B, top and bottom. This is our original SU2, and we combined this to have SU3, but now I am shifting a little bit. I am writing these also doublet. Why? These are the doublets of the standard model and not the doublets of the original SU2. But anyway, forget about that. When we come to standard model, we will talk about that. So the 6 quarks form 3 doublets, and the 6 leptons also form 3 doublets. Remember, for leptons, obviously there is no isospin, and still I write them as doublet. So obviously this, if at all it is a doublet, it should be doublet under a different isospin like group. All these on the very first lecture I had talked about 3 quark doublets and 3 leptonic doublets, and we should really put U alpha, D alpha, C alpha, S alpha, alpha going over 1, 2, 3, that is color if you want to make it complete. So remember, the the quarks are not 6 in number, it is 6 into 3, 18 in number actually if you count the colors separate, whereas leptons are only 6. Let me say a little bit about mass of these objects. Masses in MeV. This I already mentioned, 4 MeV, and this is about 8 MeV. And this I already said. I forgot to mention the psi quark, I mean the psi bound state, remember, was 3.1 GeV, and it's a bound state of C and C bar. And so each C and C bar is about 1.5 GeV, a little larger than 1.5, let me put 1.6. And then there is a binding energy, so that the full bound state is 3.1 GeV. Sum of 1.6 into 2, 3.2 minus the binding energy. These are all approximate numbers. You have to go to more detailed calculations in order to write more precise. Upsilon was about 10 GeV. I don't know whether I mentioned it. This was seen as a resonance at 3.1 GeV in E plus E minus collision. This was seen as a resonance at 10 GeV. So this is bound state of B and B bar. So and their masses have to be therefore about 5 GeV. This is about 1.6 GeV. This is about 5 GeV. I already mentioned. See how much mass difference is there between these. The third one, T, the top quark is 174 GeV, and this is about, I think I made a mistake here, 1.6. This is S. I already said S mass is about 30 MeV. This is GeV. So 1600, and so here I have to put 3 zeros, and this is 5000. And here nu E, so ME mass is very small. We will discuss it separately. Less than electron volt, 1 electron volt. Electron is 0.51 MeV, and nu mu 1 electron volt. This is also less than 1 MeV. The masses are a little different. Nu mu masses. Actually, there is a complication about discussing the masses. I will come to that later, but these are approximate statements. And mu is how much is it? About 107, is it? 107 MeV, and tau is 1700 MeV. Is also. But remember, we have been calling the proton as the bound state of U bar d, whose mass should be less than the masses of these. The masses of these 4 plus 4, 8, 8 plus 8, 16 MeV, whereas this is 940 MeV. How do you account for the mass, such a big mass? Most of the mass, pardon me? Oh yeah, I am sorry. UUD, yeah, thank you. Most of the mass of P and similarly neutron come,
Slightly bigger letter.
yeah, come from the glue field. Proton and neutron are not simple composites of U and D. It is surrounded by a very intense glue field which has energy, and converting it into mass, it gives you this 940 MeV. Since most of the mass of all matter comes from the mass of the nucleus, and hence the mass of the proton and neutron, you see most of the mass of all the objects which we see come from the glue field, the gluonic field of QCD. Of all visible matter. This is a very strange thing, but it is true. Here I want to point out an analogy. After J.J. Thomson discovered the electron at the end of 20th century, 1896, end of 19th century, right? 1896 or 1897, he proposed a model for the electron, and he thought that the electron mass me comes from the electromagnetic field, actually electrostatic field. Electrostatic field surrounding the electron, because electron is a charge surrounding electron. He made the calculation, and he found that this will require electron, if it is a charged sphere, will have a radius. This is called the classical electron radius, or E is equal to I think it is of the order of fine structure constant divided by the mass of the electron, and if you compute it, you will find about 10 power minus, a precise number can be worked out, all these coefficients can be worked out. If it is a sphere charges distributed uniformly, it will come to 10 power minus 13 centimeter. So, that was J.J. Thomson's classical theory of the electron structure, but obviously this is wrong. He used only classical physics, because this was before the days of quantum mechanics, 1896, 1897, and at such short distances quantum mechanics has to be used and will play an important role. So, this is completely wrong. Nevertheless, this name classical electron radius has stuck. People who learn electromagnetism, I hope you have learnt this point. So, it was not correct for electron, but it turns out it is correct for the proton, but not with the electrostatic field, but with a glue field. That is what I wanted to point out. So, that is more or less particle physics at one level, we can say. Not everything is completely explained, but to some extent. Now, in order to go to still higher level of learning, you have to know a little bit of quantum field theory. So, briefly in the rest of the time, I will say a little bit about quantum field theory. I will come back to it later, but for the moment let us do a little bit now in the remaining 15 minutes or so. I hope these are all qualitative things and easy to understand. Now, what I am going to say now will be a little harder, and I already mentioned a knowledge of quantum mechanics, even relativistic quantum mechanics with relativity thrown in, is absolutely essential in order to understand what I am going to say. But if you do not know it fully, I will give some preliminary ideas, and I understand Sunday classes are going on, given by Satya and Joseph Prabhakar. So, those people can ask them to give some lessons on relativistic quantum mechanics, relativity and quantum mechanics. Usual quantum mechanics, I assume that all of you know, non-relativistic quantum mechanics based around Schrodinger, Heisenberg, but the Dirac equation is essential in order to go further, and for that relativity is necessary. So, some amount of relativity, especially the relativistic notation, 4-vector notation and so on, and how to write even electromagnetic theory, which is already relativistic, because remember Maxwell's electromagnetic theory does not suffer from non-relativistic physics. It is relativity. It is Maxwell's relativity theory which gave rise to relativity itself. So, Maxwell's theory, but it is usually written in terms of electric and magnetic fields. It looks non-relativistic, but it can be reformulated in terms of relativistic notation. I think I will do that also. And then in Dirac equation definitely requires relativity. Schrodinger equation is non-relativistic. The corresponding quantum mechanical wave equation for electron was Dirac equation. So, I will say a little bit of these, not only these things, but how to make them quantum fields. The electromagnetic field has to be quantized, the Dirac field has to be quantized, and photon is only the quantum of the electromagnetic field. Electron and positron will come out as quanta of the electron field. This I already mentioned in my first lecture, but I will illustrate it with a few more things. But this is not a complete course on quantum field theory, that will require a full semester or even 2 semester courses. Anyway, we will do whatever we can do. Some notions of quantum field theory. Because to go further in particle physics, we need this. You might see that whatever I did in particle physics so far is very qualitative, except for the mathematics of SU2 and SU3, everything is qualitative. In order to make precise calculations, you need quantum field theory. So, that is the next step we are taking, not fully, but at least in a preliminary way. Some notions of quantum field theory, especially to discuss weak interaction, this is necessary, because after this I am going to weak interactions. QFT is the only correct language for particle physics. Remember, I already mentioned standard model is the correct theory of particle physics, and standard model is written in the language of quantum field theory. So, the main point is field is quantized. When you say quantum mechanics, you normally mean quantum mechanics of particles, namely the electron motion is quantized, but here the field, the electromagnetic field itself is quantized. And the electron field, the Dirac wave function, we will reinterpret it as a field, exactly like electromagnetic field. Just as we quantize electromagnetic field, we quantize the Dirac field also. Quantization of the electromagnetic field leads to photons. Quantization of the Dirac field will lead to two kinds of particles, electrons and positrons. So, that is the summary of the whole thing. Now, how do we quantize? Yeah. Yeah. Question? Any question? I thought there was some question. Okay.
There was no question, only your voice was echoing.
Oh, echoed. This echoing is coming still, huh?
Now it is fine.
Okay. Any dynamical system is quantized by using the so-called Heisenberg commutation relations. What are they? Qi Pj commutator is I h cross is h over 2 pi, Planck's constant divided by 2 pi. These are called the Heisenberg commutation relations. How do we get them? Q are the coordinates, maybe for a single particle it is just the 3 coordinates. P can be regarded as the momentum of the particle, but more generally coordinates are the dynamical variables in terms of which a theory is written. For electromagnetic field, the electric and magnetic field become the coordinates. Actually, it is not the electric and magnetic fields, but the potentials from which electromagnetic field is derived. They are functions of x and t, and so it is not one coordinate, infinite number of coordinates. Electromagnetic, a field contains infinite number of coordinates. Each of them denoted by qi. You can call it q as a function of x, x continuous infinity of coordinates. And how do we define momentum? I will come to that. And so q's and p's become operators. That is what is meant by quantization, become operators satisfying these commutation relations. Since they do not commute, they cannot be numbers. In classical mechanics, these are numbers. In quantum mechanics, they are operators. That is all quantization is. So, what is Pi or Pj? For that, we have to start with Lagrangian. Lagrangian is the basic object in all dynamics, whether it is classical dynamics or quantum dynamics. classical dynamics, I hope you already know how to formulate them in terms of Lagrangian. Newton's laws are not enough. To go further, we have to reformulate Newton's law in terms of Lagrangian, and it will contain the coordinates and their velocities. Lagrangian is a function of the coordinates and their time derivatives. Dot means a time derivative. And from that you define momentum by differentiating the Lagrangian I don't know why I wrote curly L. Normally for particle mechanics it is L, but in field mechanics, field dynamics, it becomes Lagrangian density, which is integrated over space. So let me straight away use L. If you in the field dynamics, these are all functions of x, and if you integrate over d cubed x, it becomes capital L, which is the Lagrangian corresponding to particle dynamics. Pi is obtained by differentiating this with respect to the velocities, corresponding velocity. That is the definition of momentum. Qi is given here, Pi is given here. These are all numbers in classical physics, and in quantum physics they become operators satisfying this. That is all quantization is. So let us start with the simplest examples. I will not work out all the consequences fully. None of my equations will be complete. By looking at some books, you can write down the more complete equations. Many times my factors will not match and so on, because I am only giving a sort of qualitative description of quantum field theory, whatever you may mean by that. Because even to discuss some particle physics like weak decays and so on, this elementary discussion of quantum field theory is needed. Now, one remark about relativity, special relativity. We are not going to general theory relativity at all. In relativity, remember things have to be formulated in such a manner that they are the same in all frames, moving with uniform velocity with respect to each other. And that can be conveniently mathematically formulated if you reorganize all your physical quantities in terms of 4-vector notation. For instance, the coordinate of a particle, instead of xi, I will use x mu. The time at which the particle is observed, and the position, a 3-vector, are combined to form a 4-vector. This mu goes over 0, 1, 2, 3. x0 is nothing but t. This 4-vector notation will be consistently used hereafter. This is only a notation, but if you all our fundamental equations should be covariant with respect to this notation. If left hand side is a vector, right hand side has to be a vector. If the left hand side is a tensor, right hand side has to be a tensor. If the left hand side is a scalar, right hand side has to be a scalar. Scalar with respect to this 4-dimensional operation. If that is true, then your theory, which you are writing down, will be relativistically correct. That is the point. So mu goes over 0, 1, 2, 3. Let me give an example. Electromagnetism. All of you know Maxwell's equations, I assume. Let me write them. They are formulated in terms of electric field. Again, 4 pi, etc. I do not know. Charge density. This is the Gauss law, which tells you how to calculate electric field. Revise your electromagnetism also. Assume that you are all MSc students, so electromagnetism you have to know. And then del cross E plus there is a 1 over C, I think, d B by E is electric field, B is magnetic field. So this is Faraday's law of induction, this is Gauss law, and there is a Gauss law for magnetic field also, but right hand side is 0 because there are no free monopoles, magnetic monopoles so far discovered. The last one is Ampere's law. Maybe here it is minus 1 over C dE by dt equal to current density. Tells you how to calculate magnetic field from current, but Maxwell added this important displacement current term. These are the famous Maxwell laws. Now you can see this is not consistent with what I said. This looks as if it cannot be consistent with relativity, but it can be rewritten. The same equations can be rewritten in using the 4 vector notation, 4 vector and 4 tensors. That is obtained like this: Fij, I and j Latin indices always 1 to 3, and the Greek indices always you have to include 0. Fij equal to, again the epsilon ijk, which we already know, Vk. This is antisymmetric, so there are only 3 independent quantities, which are the B's, and Fi0 is nothing but electric field. This is complete identification, because F0I is minus of this, because remember these are all antisymmetric. Introduce F mu nu, mu nu antisymmetric. In mu nu they are antisymmetric. So antisymmetry of Ij is automatically there. Here also antisymmetric. So complete specification of electric and magnetic field. In terms of these fields, we will be using these fields. Antisymmetric. This is an antisymmetric. Any once you put 2 indices, it becomes tensor, and this is a vector. These can be written down in terms of potentials, and in order to go further in the theory, you have to introduce potentials. Fields are not enough. You might already know that Schrodinger equation of a charged particle in the presence of a magnetic field cannot be written down in terms of magnetic field, cannot be written in terms of electric field. P minus Ea by C, A is the vector potential. You have to introduce vector potential. Similarly, you have to add to the Hamiltonian the vector, so the scalar potential. And differentiating the scalar potential, you get the electric field. Taking the curl of the vector potential, you get magnetic field. All these are preliminary things before we go further. So you go to your electromagnetism book and verify these things, whether you understand them. So in terms of potentials, you can write the electric field, you will say, is minus gradient of a scalar potential, but again we have to organize these into 4 vector notation. So the scalar potential, which we normally write as phi, I will call A0, because it becomes the 0th component of A mu, and the spatial components of this are the usual vector potential, but in general this is not complete. We have to also write 1 minus 1 over C or plus, I do not remember, please check, dA by dt. The spatial derivative of A0 and the time derivative of this give you electric field, and magnetic field is simple, which you already know, curl. Okay. Try to write these in terms of the potential. That is a very good exercise for you. The equations become simpler already. So this can be converted into equation for F mu nu in a very simple form. F mu nu is equal to d mu. If I write like this, it means bigger, huh?
No, below.
Below. This is my notation for d by dx mu. See, there is a contravariant, covariant complication is there. I will not talk about it right now. Maybe later I will talk about it. It is only a minor complication. It does not add much to the physics, so I will not talk about it. But when it is absolutely necessary, I will define contravariant and covariant. If you write mu below, it is called a covariant vector, and x mu is called contravariant. And this is called covariant. These are all notations only, and they are related by this equation G mu, x mu is related to x nu above by the metric tensor. This is called metric tensor, which is a 4×4 matrix, 1 minus 1 minus 1 minus 1 0 everywhere else. So you can see what it does is all the spatial components get reversed between the covariant and contravariant, whereas the time component does not get reversed. So that is all this, and this is necessary in order to use the relativistic notation completely. So d mu, since I have written above, it is contravariant, and that is my definition, d by dx covariant. If you differentiate with respect to covariant x, I define it as a contravariant d mu. This you can show that if this is covariant, this is contravariant. All this can be shown, can be derived. Okay. I don't know whether I should go any further. Maybe another 5 minutes I will introduce just 2 equations, but in order to make sense I have to say much more. At least the electromagnetic field I can say right now. For the Dirac field I will do it next week.
We can continue.
Pardon me?
We can continue in the next class.
Okay, then I stop here. So I have just got some preliminary definitions and so on to make you in order to make use of it, in order to construct some quantum field theory. I will give examples of how to construct quantum field theory of the electromagnetic field and the Dirac field. Okay, that I will do next time. Okay, but if there are questions, you can ask me.
I want to understand this deep inelastic scattering experiment.
Yeah.
This electron proton that collision.
Yeah.
When I compare this with the electron scattering experiments to find the size of the nucleus.
Ah. Yeah, but those were lower energy, lower momentum transfer.
Yeah, but I think when people were trying to find the size of the nucleus.
Yeah, in fact that was Hofstadter again at Stanford, I think. He also got Nobel Prize, I think. The size of the nucleus was experimentally determined by studying electron nuclear scattering. Yes, those were earlier, 50s, I think. Then
yeah, you assume there is some kind of Rutherford scattering.
Yeah, that was called the Rosenfeld formula and so on. Correct.
And then when the cross section deviates from the Rutherford scattering, you see that
there is a form factor, an electric form factor and magnetic form factor in terms of q squared, and they roughly correspond to the Fourier transform of a physical object of size 10 power minus 13 centimeter or 10 power minus 12 centimeter, depending on which nucleus you use. Yes, those are very important experiments.
So the principle based on which this asymptotic freedom is discovered is also similar?
No, it is very different now. Now the energies are much higher, and now now we do the experiment on proton itself. First I think Hofstadter did it for proton also, the elastic scattering of electron on proton. That is elastic scattering, remember? And that elastic scattering gave the form factor for the proton, the electric and magnetic form factor of the proton. But now you increase the energy of the electron to much higher, those may be MeV energies, maybe 100 MeV. Now these are GeV energies, the Stanford linear accelerator, which accelerated the electron to much higher energies, and the energies are so high that a large number of hadrons, this is not elastic, this is inelastic, deep inelastic, so many particles were produced. So this is a much more complicated process, not elastic scattering. Elastic scattering will measure only the size, nothing more, and that is done. So you have to go to inelastic process, and that inelastic process, although it is very complicated, it becomes simplified through the identification of the constituents of the proton. This is a very important thing, I already mentioned it, I think. See, the story of the discovery of the quarks is somewhat like the discovery of atoms. in all of physics. Remember, Boltzmann suffered a lot in trying to convince, chemists were already convinced that all matter is made of atoms. Physicists did not believe, physicists and some philosophers, Mach, Oswald, etc., pounced on Boltzmann's neck, saying that atoms are only a mathematical fiction, they don't physically exist. And Boltzmann used the atoms to convert the whole of thermodynamics into the mechanics of atoms, moving atoms and molecules. And people like Mach did not like it, they went on fighting, and in fact Boltzmann committed suicide. I don't know whether he committed suicide because of this, because all this opposition certainly affected his mind. He committed suicide because of mental illness and so on. But anyway, finally physicists began to believe in the existence of atoms only because by using Einstein's formula for Brownian motion, which showed how the kicking of the atoms or molecules in a liquid make some small suspended particles move. That is called Brownian motion, and he gave an exact formula for this. And Perron, French physicist Perron, did experiment, verified Einstein's formula, and showed that the Avogadro's number which comes in Einstein's formula agrees with the Avogadro's number determined by physicists and chemists earlier, and that convinced the people that atoms are real. They are not seeing atoms, but they are seeing the kicking motion of the other bigger objects kicked by the atoms or molecules. So in quark story also it is somewhat like this. That is why, although Gell-Mann himself, I remember I described the story, the Bangalore event and so on. Gell-Mann himself was very tentative. When he finally took courage after 3 years after the Bangalore event to publish a paper on quark, he was very tentative. He did not publish it in an American journal, Physics Letters. He published it in Physics Letters. What was it called? I think it was called a tentative theory of hadrons, something like that. I just forgot the precise title which he had given. Because he thought that Physical Review Letter will not publish it, he sent it to Physics Letters, got it published. And so in the case of quarks also, it convinced the people. There were some people who were convinced that quarks exist, like Dalitz and A.N. Mitra in our own country, Delhi University man. These people worked on quark model even before other people were convinced. But most people got convinced only after the deep inelastic scattering experiment, and also the psi particle discovery. Psi clearly showed that the psi hadron is a bound state of two quarks, quark and antiquark. And deep inelastic scattering definitely is the turning point in the history of quarks. So the analogy to the story of atoms is quite striking. Yeah, you are right. I mean, Hofstadter and company determined the size by doing elastic scattering of electron, but now I am talking about inelastic scattering, which probes further. Okay?
Yeah.
So we will meet next week.
Hello, sir.
Hello?
Sir, I have a question.
Yeah.
Sir, you wrote the masses of those quarks and leptons.
Yeah.
And earlier you also told that Gell-Mann predicted that omega minus particle, and it was
Yeah.
related.
Yeah.
When do you say that it is like he predicted?
Yeah.
Predicted, and when the particle was discovered.
Yeah.
How do you know that it is that particle?
Oh, because the characteristics of the particle were identical to what he had predicted. Because it had to decay, omega minus had to decay, and another thing that gives me an opportunity to, I forgot to mention one point. You remember, that is again Satya's question earlier. Why is it resonance? How can resonance be same as particle? I gave the example of deuteron and neutron, but a more pertinent example comes to my mind now. So remember the tenfold multiplet. Just go back in your mind the tenfold multiplet. See, that was a what was it called? Delta. 4 particles, and then delta mass 1232 and this is 1380. And a cascade. So this was all known, and he predicted that there has to be another particle, a singlet omega minus, and he had already worked out the equal spacing rule, mass formula, and these differ by about 140 or 150 maybe, and adding that he predicted mass. So the particle was found exactly at this mass. Not only that, omega minus decays into, I think cascade minus pi 0 is a possibility, for instance. So these decays were seen. Let me write down one more. Sigma minus maybe K0 I can put, K0 bar I can put. All these decays were seen. And more importantly, these decays were weak decays with a lifetime of about 10 power minus 10 seconds, typical of weak decay. Remember, this decay by strong interaction, delta goes into nucleon and pi, sigma goes into, I don't know what it goes into, sigma will go into lambda plus pi and so on, and this goes into, cascade goes into sigma, cascade is strangeness -2, so sigma, I think I have to put a k bar, we put appropriate charges. These are all strong interactions. This is a decay width of gamma 100 MeV. These are also occur only as resonances, they don't leave track, whereas this guy left a track. 10 power minus 10 second, I don't know, multiply by velocity of light, you will get 1 centimeter at least. So in a bubble chamber which was used to, in which it was detected, it could travel 1 centimeter and they could see it. Now the point I wanted to make was, see here we are putting all this into one multiplet, and these are all resonances. This is not a resonance. In the conventional terminology, this is a particle. So that's why I am saying resonance and particle, there is no difference. You have to regard them as same. This guy, see, if this guy has to decay into strong interactions, it has to go into let us say cascade minus, cascade and some k, r k bar. But add the masses 15, 20 plus about 500 MeV is almost 2000 MeV, whereas the mass is only 1670. That is why the guy cannot decay. It does not occur as a resonance, it decays by weak interaction, it cannot occur as a this. Because here, if it is a strong interaction, it has to conserve strangeness. Here, you see, strangeness is not conserved, that's why we are able to get away as a decay. Weak interaction does not conserve strangeness, strong interaction has to conserve decay, but then the energy conservation prevents it. So,
So sir, from the from the decay process, it can be predicted.
I mean, if the mass is 1670, these are the possible decay modes, and they will be weak interactions. So you can see the track. They saw the track, measured the lifetime, and what are the various decay modes, what are the branching ratios. Everything was measured. Everything was consistent with this. But one thing they could not do. See, all this, if they have to be put as one multiplet in SU3, they should have the same spin parity. These all these have spin parity 3/2. I already discussed it. Three half plus. This guy at that time they could not determine the spin or parity, and it took many years. Only recently, I think, this was experiment was done in 1965, I think, but maybe only after 2000, maybe 40-50 years, spin parity of this also has been determined. So that was missing, but there was no doubt in people's mind that this is really the particle predicted by Gell-Mann.
In standard modeling,
Yeah.
those differences for the mass of the particles.
Yeah.
Those are that we have got from experiment, right?
Which experiment? Which particle?
Like all the leptons and
Yeah, those were all experimentally determined. Electron, muon, tau.
Masses were not.
The quark masses were very indirectly determined. The U and D quark mass, I said 4 and 8 MeV. How do you experimentally determine? It's very hard because it's very strongly interacting system, and so it's very hard, and some very indirect things and some further theoretical structure like chiral symmetry and so on has to be used in order to derive the mass of the light quarks UD and even strange quark MS. All these three were determined using a combination of theory and semi-empirical data. Whereas the masses of a T quark immediately comes because T decays only by weak interaction. By adding the final particles you can get it. Then charmed quark was very easy because just essentially half of the mass of the psi particle, and B quark also essentially half of the mass of the upsilon hadron. So some are easy, some are difficult, but by now all of them have been determined experimentally.
So is there any way right now to predict the masses completely from theory?
Oh, that is a very good question. Nobody knows. All the masses of the particles have to be put by hand into the standard model. That is a very good question, but answer is no. That itself shows that the standard model cannot be the final theory, or people talk about final theory and so on. I don't believe in final theory, but the next improvement of the standard model might tell you what the masses are, but nobody has any idea. Although people are theoreticians are working on it, but there is no consensus. Nothing definite is known yet about how to get the masses. The masses are the most important unknown. Experimentally determined masses have to be put into the standard model, that's all. No mass can be predicted. Whereas hadrons in principle can be predicted from the masses of the quarks because of we know the interaction QCD, but QCD is such a difficult interaction that also turns out to be very difficult. Except in a few fortunate cases like psi. Psi is more or less a quark and anti-quark interacting through a gluon exchange, and people have computed it, and they are fairly successful. But other hadrons like pion, kaon, and sigma or lambda particles or nucleon, starting from the quarks is very tough. But there is a way of version of theory called see, QCD is a very complicated theory because it is a strongly coupled theory. And for such theories, now there is a method called the lattice gauge theory. Put the theory not on continuum of space and time, but on lattice points. On the lattice, there is a way of regulating even the divergences, and you can get the results. And that is a very big industry going on. Lattice gauge theory started by Wilson 50 years ago. Now it has progressed into such a big level that they claim that everything in hadronic physics can be computed in terms of the QCD, using QCD. But that is a very big field.
So apart from the masses,
yeah,
other properties, those isospin.
Those are simple. Those are simply add the isospins of the constituents, you get the isospin of the hadron. There is no problem about that. Mass is the complication. Mass and sometimes even the spin parity, because spin parity also depends on the dynamics. But otherwise, the internal quantum numbers like isospin, strangeness, or hypercharge, they are the easiest thing to do.
One more small thing, sir. Sir, how do you know that these six are the only quarks or six are the only leptons?
What?
Right now we have 6 leptons and 6 quarks.
Yeah. How do you know that these are the only ones? We do not know. As of now, from the highest energy collider, we have not produced anything new, although sometimes some suggestion is made about these 3 columns which I had for quarks and leptons, they are called the families. 3 families are 3 generations. We know these 3 exist. Whether the 4th family exists or not, we do not know, but my guess is they do not exist. The reason is actually, I cannot go into details now. If there is a fourth quark family and a corresponding fourth leptonic family, then there should be a fourth neutrino. There is very good evidence that no more neutrinos apart from the 3 exist. That is because of the Z boson. From the Z boson width, Z boson also goes into nu bar, and the width will be much more. That's called the hidden width. The hidden width which we do, invisible width. The invisible width can be calculated from standard model. It agrees with the experimental number fantastically. If there is one more neutrino, the Z width will be larger, and that rules out fourth neutrino does not exist. So the fourth columns don't exist. It's a very indirect argument, but it's a very good argument. Standard model is not complete at all. I never said it is a complete model. At the present stage of the knowledge, that is the best we have, and it correlates all the data. Any experiment done in LHC up to 14 TeV center mass energy agrees with standard model. In fact, constantly they are trying to break the standard model by seeing whether everything agrees with the theory. But nobody has found out. Sometimes some signals of breaking of standard model does not agree with that particular decay mode, particular branching ratio, that particular cross section comes out in and we discuss it in seminars, but after 6 months it disappears. Standard model has proved so robust, nothing more has been seen. In some sense it is very good. It shows how successful the theory is. Another sense it is unfortunate, because we know that standard model is not complete, because it does not have explanation for masses. So, but we are not able to go further to find out what is that further thing. I mean, hopefully further experiments will suggest. Because we know that there are better theories than standard model, like the supersymmetric theory which I mentioned, or grand unified model, or ultimately superstring theory. All these things are better theories. They may even superstring theory in principle, since it contains everything, no other free parameter. Superstring theory, one great advantage is it does not have any free parameter. So all the masses of the particles which come in standard model and the coupling constants are derivable from theory in principle, but that is a dream. Nobody has constructed the superstring theory in such great detail as to be able to do it. Okay?
Thanks, sir.
Yeah. So we will stop here. We'll meet next week. Okay.